Okay, let's continue with more on protein function. So what are the key ideas and terms to determine protein function? So from previous video, we know that protein can bind a ligand or another protein, okay, based on the binding site, and there has to be a binding site for it to bind. For an enzyme, as an example, the ligand is actually a substrate, and they bind in what is called as the active site. So binding site and active site, I will explain more when we go into the bioinformatics part in a few weeks time. So basically, ligand has to be in the correct shape. Apart from that, ligand also has to have the complementary charges or hydrophobicity or hydrophilicity to the protein that it has to bind to. Now, this is more or less, you'll see this when you learn about enzyme in enzyme tech, but a lot of binding in enzyme is basically based on lock and key. But in terms of protein function and protein binding, there are two hypotheses. So the first is lock and key. Second one, which you will see in a while in a few slides, is actually the induced fit. So in a lock and key hypothesis, so I think you can imagine, as the name says, lock and key. When you put in your key to a lock, when you turn it, you can open it up if the key is the correct fit to the lock. Okay, so if you go and look at your key, well, the old key anyway, so you will see that there are kind of like designs or indentation and whatnot on the key that fits to the lock. So your key is kind of like your substrate. Your lock is kind of like your enzyme. So the jagged or basically the design, okay, the pattern on your key that fit to your lock is actually the active site. So it has to have a good fit. So once it fits, then only basically you can turn your key, and in this case, okay, they could produce a catalysis product. Okay, so catalysis or basically anabolism or catabolism. So this is basically true for antibodies. And well, we'll see again the difference between polar and nonpolar, as you can see over here. And this is again the difference between them in terms of how they will bind. Right? So don't worry too much. Now the second one that I was saying, the hypothesis, is the induced fit. So induced fit is kind of, have you ever heard of a master key? So which means that a master key could open any key, or a master key could open any lock, and there is no problem of you trying to find the right or the correct key for a certain lock. So this theory is kind of like an induced fit theory, okay, whereby the enzyme, of course, okay, or your lock, okay, has a certain kind of shape, kind of a binding site for it, but again, the key, the master key in this case, and your substrate basically don't. But what happens is that they could still fit in each other because the active site wrapped around the substrate molecule, to induce fit. So that means that the enzyme itself, is not your substrate. The enzyme itself, try to fit in, with the substrate, and more or less similar mechanism for your master key as well. So in terms of ligand binding, this is how it occurs. So your ligand, or any kind of molecule, and it has to bind to the binding site. So if it fits directly, so that means that, well, it should be no problem. That means that there is a lock and key hypothesis. But if you have an induced fit, again, what happens is that so usually we know that it doesn't really fit that well. So the enzyme will produce covalent bond, try to bond with the active site, with the ligand, to make sure that it could hold on to the ligand and produce catalysis. Now, formation of this binding site, is basically when the amino acids form within the protein. And this is formed when the protein folds. As the protein folds, so the binding site is actually being formed along the way. Hence, you will see why protein folding is actually important. Apart from just giving the protein its structure, basically it also determines the binding site with a ligand or another protein. And the remaining sequences may also play a role in regulating the protein's activity, especially those amino acids nearby it, or opposite of it. Sometimes it could play a role in the binding. Now let's have a look at the example of antibody family. So in the second video, I was telling you that antibody has the shape of a Y. I think I have it in the next slide. So again, basically, the Y-shaped molecules have two binding sites, and I think you will remember from your old times that basically the Y shape, the top one, over here, is the one that binds to it. So the loops of polypeptide at the end of the binding site are what imparts the recognition of the antigen. So we know the antibody binds to antigen. So changes in the sequence of the loops make the antibody recognize different antigen, and thence that would determine its specificity. Alright, so yep, this is what I was talking about. So the Y shape again, and we know, okay, this is basically the binding site. Not anywhere here anymore, okay, but it's here. And as you can see over here, you can see the S. So disulfide bridges basically are here, and there are domains within the antibodies. And in actual, even though we imagine, or basically if you look at the cartoon diagram of antibodies, it looks like a Y. In actual, okay, the protein structure actually looks like this. Ugly, right? But again, if you look at it like that, yeah, but if you have a nice carbon structure, usually it's quite nice, okay? Almost similar like this, it's just that you have to turn it around to find the perfect spot. Now, let's move on to enzymes as catalysts. So we know that for catalysts to occur, we need an enzyme. So they are also protein enzymes, okay, and they bind to the ligand, and probably they have a specific ligand, or sometimes they could also bind to general ligand. So this is the first step, okay, in the process. So the ligand is also sometimes referred to as substrate. We know that as much, and it could be just one or more than one molecule that could bind to it. So the output of the catalysis, okay, is basically a product, okay, that is produced either from the breakdown or from the basically combination of it. So enzymes can repeat these steps as many times, and basically rapidity, it depends so on the availability and also the condition of the environment. And this active site, the binding site, okay, which is very special, okay, in enzymes. So this is the one, okay, that is specifically only for the binding with a specific substrate. Hence the difference between binding site and active binding site. So more or less just to refresh back your mind, okay, and hopefully for you to catch on enzyme catalysis. Okay. Now, we know that in catalysis there are two reactions: anabolism, anabolic enzyme, and also catabolic. So anabolic is when you break down or basically you formed. So if you see here, okay, sucrose is synthesized, okay, in organism from the simple sugar, which means that you make a product, okay, anabolism. So in catabolism, it is the other way around, the breaking down. Right, so in terms of enzyme activity, the number of substrate that is converted to products is basically depends on per unit of time. And we can change the stability of this enzyme to work in two ways, okay, either through denaturation or inhibition. So don't be surprised to see denaturation or inhibition here. So what do they do? How would they affect the enzyme activity? Now, for denaturation, so denaturation is also a form of protein unfolding. For example, cooking an egg. So that is, okay, meaning that you, well, if not, then probably you would want to eat a raw egg, okay? So cooking it, making it bearable to eat, okay, but it also causes protein to denature. Now, if an enzyme loses its secondary, tertiary, or quaternary structure, it is called as denatured. Usually, primary structure is not affected because it is just a polypeptide chain, so it will remain as it is. Now, denatured proteins lose their active site because as it unfolds, there is no more binding site or active site because it has been unfolded. And of course, it could not catalyze reaction. It would also reduce enzyme activity. For example, heat can disrupt hydrogen bond, disulfide bond, and also hydrophobic and ionic interaction. Apart from that, high or low pH can also disrupt ionic bonds and hydrogen bond. So as you can see here, disulfide bridge or bond, as strong as it is, it could also be affected by high heat. Now the second affecting factor is the inhibitors. So it prevents enzymes from functioning, as you can see from the diagram. So you can get two types of inhibitor, competitive and non-competitive. So competitive inhibitors would sit in the active site, okay? The binding site or the active site, mostly is the active site. I'm not sure why it's not moving, okay, my cursor, never mind. So what happens is that, okay, so once it sits at the binding site, your substrate could not come in because there is a big chunk, a big block over there. So it couldn't get rid of it. But for non-competitive inhibitor, usually it binds to the enzyme and make them unable to bind to substrate. Okay, so meaning that usually for the non-competitive, you can get rid of it, okay, if you have a cofactor. But for the competitive, most of the time it's hard to get rid of it. Okay, so we move on, okay, to the protein classification in terms of the definition. So this is so you know that as complicated as protein is, but there is a rule to how it is being classified. So it is usually grouped, okay, by similar protein based on the structure, function, or size. And of course, it is also based on either its globular or filamentous or helical, and whether it is used for catalysis or for structure purposes, and the size, whether it's small versus large versus very large. Alright, so this is basically how proteins are being classified. If you're interested, you can ponder on it. Okay, so I'm not going to go further because we are not going to dwell too much on this because ours is on proteomics, so we will see in terms of the technology. Now, so that would be it for the third video. Move on to the fourth video, whereby I will introduce you to the proteomics.